SwayamPrabha. Digital India. Educated India.
Good morning, friends. Now again, fly the aircraft and try to understand whatever we have designed, whatever configuration we have laid out in an aircraft, and the aircraft is flying. Is it possible to validate whatever we have designed, we are achieving the same? Or indirectly or directly, I am asking a question, can I estimate the drag puller of the airplane through flight test? Okay? That will be the thrust for this lecture. Before we do that, let us recall we started with aerofoil. Right? They are basically contours with an infinite span, infinite aspect ratio to ensure the flow is always along the chord. And wings are composed of, if you take any cross section, you will get the aerofoil shape. Okay? Please also understand that it's not necessary that same aerofoil will be used at every location along the span of the wing. We will try to know, if time permits, how do I decide where do I put what type of aerofoil. Okay? Now suppose you ask me a question, how do I generate CL, two-dimensional CL versus alpha for aerofoil? Do you think you have asked me a complete question? Is it a correct question? No, it's not a correct question. Question is not complete. The question should be, how do I generate CL versus alpha for different Reynolds number? Right? Reynolds number. This is important because we know that CL depends on Reynolds number also, and very importantly, yes. So if you now ask me second question, how do I generate experimentally? Because after aerofoil shapes are infinite span, as I tried to explain. But remember, why do we say infinite span? We say infinite span because we do not want any flow to go like this or any flow to come like this. That is why we model it as infinite. So what is the practical, pragmatic way of doing it is, go in a tunnel and end to end you put a wing which is having shape like this. Contour is decided by the aerofoil, and now you have made the whole wing is just touching the wall of the wind tunnel. This is the wind tunnel test section. Okay? Test section. And air is blowing like this. If the wingtips were not touching the wall, then it would have behaved like a finite wing. But there is a gap, flow will come like this. So by ensuring that they are touching the test section wall, we are avoiding that. But barring some effect here near the wall, which is wall effect, which can be handled through calibration, mostly the flow will be along the chord, a two-dimensional flow, and it is what is consistent to our understanding of an aerofoil. So I will put a load balance, I will go on measuring CL for different angles. But since it is for Reynolds number, so I must ensure what is that angle and what is the Reynolds number. So I can go on generating different values of CL for a given angle, and I go on changing the Reynolds number. Okay? I can change the Reynolds number by changing speed, by changing density of air inside tunnel, So many combinations are there. I can change the Reynolds number. So typically if you see database of aerofoil which will give you the CL, CD characteristics for different aerofoil, they are being generated through experiments, right? And each aerofoil is nomenclatured depending upon what is its nose radius, what is its thickness to chord ratio, right? There is a standard nomenclature. We will try to address that nomenclature before I come to some aspects of design. Okay. But if you see this CL versus alpha graph for any aerofoil you pick up, you'll find it is given something like this. And here, for different real number 1, real number 2, real number 3. So you'll find same alpha, okay, same alpha, but depending upon Reynolds number, the CL value will go on changing. Correct? So this is very, very important to capture and make your understanding very clear. Once you have knowledge about this aerofoil to wing or finite wing, we know how CL alpha of the wing is related to CL alpha 2D of aerofoil. This is something by CL alpha 2D by pi aspect ratio E. This is already we have done. So we do this correction and try to find out the total CL of the airplane by estimating CL of other components as well. But I am only focusing on the wing. And same thing can be extended directly for tail also. But we are talking about drag puller, so we'll try to understand a little bit on drag part also. Very small part, very important part. If you see 2D aerofoil data, we'll also see that the data sheet or the database gives CD versus CL something like this. Some are something like this, depending upon what type of aerofoil you are using. Okay? That is depending upon type of contour you are using. What is the maximum T by C? What is the leading edge radius? All such issues are there, right? And you can customize your aerofoil, right? But what is important here, if you see as CL is increased, let's say this, if I consider this part, I am saying there is a increment in CD. Okay? Almost it gives almost like a, maybe may not be correct, but almost like a quadratic. But it's not a correct statement. But trend wise, you may see it is almost quadratic. So what do you think? Is this because of induced drag? That is my question. Is it because of induced drag? That is my question. Okay? Please understand, I cannot talk of induced drag when I am talking about aerofoil. Be very clear, because it's an infinite span, so there is no question of finite wing effect. So this trend of increase in CD because of increase in CL should not be interpreted as contribution because of induced drag. Correct? For 3D, for a wing, we have seen CD and CL graph goes something like this, you know. And this part, all these things, as increases because we talk, this is because of KCL square term. CD naught plus KCL square. That is the drag puller. But when I see a 2D aerofoil, the caution is this increment is not because of induced drag. This is primarily due to the flow separation. And this is a complex field, right? Okay. And people are working in this. I have been talking to one of our honored researcher. So, and I could get this feeling that yes, a lot of fundamental work is also going on into this. This is one, right? Second part, you will see some aerofoil data where CD versus CL have a bucket type shape. We call it drag bucket. drag bucket. Okay? What is the significance of or importance of drag bucket, or how can I use this? You see one thing, if I am flying the machine CL close to this drag bucket zone, then there is hardly increase in CL because of this. Okay? But if I am flying somewhere here, then I will have unnecessary increase in CD because of increase in CL, in addition to induced drag. That is something different. Okay? So a good designer will try to select the CL so that I am operating somewhere in this drag bucket. Or if it demands that standard aerofoil is not able to fit that requirement, then you customize your aerofoil. Okay? Knowing this now, we want to estimate drag puller through flight test. Now it is something like this. You are given an aircraft, you are a pilot, and it is told to you, go fly and find out, tell me what is the drag puller of this airplane. So what we should do, we know one thing, that if I cruise, then thrust is equal to drag and lift is equal to weight. We are so much using this. So I multiply both sides by V. T into V equal to D into V, which is nothing but half rho V square S into CD naught plus K CL square into V. So again I write T into V is half rho V cube S CD naught plus half rho V cube S into K into CL square. What do I do now? I now know that lift equal to weight, so CL is equal to 2 W by rho S V square. Right? So what I do, I replace CL square by using this CL. So I have now expression half rho V cube S CD naught plus half rho V cube S K into 4 W square by rho square S square V to the power 4. No objection? Everything is fine? If everything is fine, try to understand what is T into V. T was what? T was equal to drag, or thrust required equal to drag. So if I want to cruise, I must ensure my engine is providing that much of thrust. What was T into V then? T into V is power available. Okay? So for our understanding, we will write T into V so that we don't get mixed up as brake horsepower, keeping in mind that this is available from the engine. This is equal to half rho V cube S CD naught plus 2 K W square divided by rho SV. Rho SV. Okay? Now what? What is our aim? Let us not forget. We want to estimate drag puller, that is CD naught plus KCL square. That is, if I can estimate K and CD naught from flight test, then I can express the drag puller as CD naught plus KCL square. That is a simple question. So my eye should be fixed to know clearly that my aim is to estimate CD naught and K. Now we do a little bit of more arrangement. What we do, we multiply both sides by V. So what I have, BHP into V is equal to half rho V to the power 4 S CD naught plus 2K W square rho S. And if I do further rearrangement, I can write, let me write separately because we will be planning our experiment based on this expression. So I have BHP into V is equal to half rho S CD naught V to the power 4 plus 2 K W square by rho S. Let us ask ourselves, what are those variables I can measure? What is BHP? BHP is engine parameter. So engine manufacturers give chart, they give the calibrations. So if you know what is the temperature outside, what is the RPM, what is the manifold pressure means the roughly it is the pressure at which the mixture is taking place. As far as BHP is concerned, I can get it easily through manufacturers chart, engine chart we call it, engine chart, which essentially tells you if I know manifold pressure, this manifold pressure, if I know RPM, I know outside air temperature, then using the engine chart, I can easily know what was the power available from the engine at that speed. If you see here, all this information you get in the cockpit, right? You have seen in the cockpit there are instruments which will give you readings for manifold pressure, RPM, and outside air temperature. Right? So this is in my control. S is the wing area, which is known. What is V? V is the true airspeed. How do I get V? I know by now that we have airspeed indicator, which gives me V equivalent. Remember, we write half rho V true square equal to half rho sea level V equivalent square. That is how the airspeed indicator were calibrated. So if I know V equivalent, using this relationship, I can get what is V true. But for that, I need information about the local density there. I know outside air temperature. So I can use this. Again, I can find out rho. I can find a true airspeed. The other important thing is W, weight. The issue with the weight is, when I go for takeoff, I'll take the weight, passenger, fuel, etc., etc. But when I'm doing the cruising, actually some fuel is consumed. And when I'm doing cruising, fuel is continuously getting consumed. So which weight should I take? So best way to do is, what I do, when I try to do an experiment, I find out how much time has elapsed. And from there, I use the fuel consumption chart and see how much fuel is consumed for that time and deduct that much of fuel from the weight. This is one way I find out. Second approach what I do, when I land, I again weigh the machine with all the passengers and then take the average weight. Okay? And you'll find they will not come very off. Okay? So this is how I get this information. But so what? Question is, okay, I can measure all these things. So how do I find CD naught and K? That is the question. If I plot graph between BHP into V versus V to the power 4, what sort of curve we will get? See, BHP, so I say Y equal to, this is I am telling X, I call it M, and this is plus C. So what sort of graph I should get? I should get straight line. Okay? I should get a straight line, and this should be my 2K W square by rho S, because that's the intercept, and the slope will be equal to half rho S CD naught. Right? And once I measure this intercept and slope, I can find out CD naught and K. This is the understanding. But how do I do it? Through experiment. Try to understand. So what we should do, we will go for a cruise flight, and then we note down the altitude. Okay, who will give us altitude? The altimeter. It will give us pressure altitude. Don't forget that. Okay. Then I note down the outside air temperature. Again, we have a gauge to measure outside air temperature. So I take this reading. Now I ask pilot to maintain a cruise with a speed V1. And what should I note down? I note down the speed, I note down the manifold pressure, MP, and RPM of the engine. These two, I note down. Once the pilot is okay with the cruise at V1, you check the airspeed indicator, whether the speed is same or not, what you are looking for. You check the altimeter, whether the height is constant or not. You check the bank indicator, whether it's level or not. You want to say yes, you note down what is V1. Note down what is manifold pressure. Note down what is RPM. Okay? Then again, you request pilot to cruise at a speed V2. Again, you note down what is the manifold pressure, what is the RPM. You do it for 3 to 4 or 5 readings. Take like this reading. And then you come down and take the weight. Touchdown. Of course, before you went for the experiment, you must take the weight of the aircraft plus passenger. Please note down, aircraft plus passenger plus pilot, total weight, and ticket. A wiser man will note down the time. He'll carry stopwatch also, because we like to see what was the time during which I was not cruising. So he will try to find out the fuel weight and reduce from total weight. Okay. So I know all these things. Now it is simple for me. I'll use manifold pressure, RPM, outside air temperature to find BHP. I will use equivalent air speed density to find V by using relationship half rho V true square equal to half rho V square, right? Rho sea level, okay? V square. Rho I'll find out through outside air temperature and standard atmosphere table. And now I will plot what I will do. So what is done? You know manifold pressure, you know RPM, you know V. So you are calculating the BHP into V. Okay? So this is V2 bar 4. You know V, so this point and whatever BHP into V you got, you get to this point like this, some points, and then fit it with a straight line, because you know that they will follow straight line. Okay? Sometimes you have to find the best fit because there is a measurement error. Once you do that, then you take the slope, and this is equate to half rho S CD naught. Let's say this slope is A, and this intercept, let it is B, and that should be equal to 2K W square by rho S. So I know half rho S CD naught, this is CD naught, equal to A. So CD naught will be equal to A into 2 divided by rho S, and K will be equal to B into rho S by 2 W square. So from there, you now know what is the value of CD naught, what is the value of K. So you postulate CD equal to CD naught plus KCL square. That is how you can get drag polar, estimate drag polar through flight test. Is it not wonderful? Right? If you happen to come to Kanpur, you are welcome. Send me a mail. We will give you an opportunity to conduct this experiment. Okay? Thank you very much.